Okay, so in Monday's lecture, what we found out was we saw that we can draw Lewis structures by basically following these series of directions or these series of steps. But what we're going to learn today is that there can oftentimes be more than one legitimate Lewis dot structure that can be written for a molecule, and the question is which one of those is truly correct? Are they all correct? Exactly how do we handle those? So we went through these steps of writing the Lewis dot structures, and again we have to just follow these rules. We're always going to put hydrogens and fluorines at the end of the molecule so that they have one and only one bond. The central atom is usually the least electronegative element, except in the case of when you have a halogen attached to oxygen, like in this case, the perchlorate ion, or the chlorus or iotis or bromous acids. Then we write the Lewis dot structures around each atom in the structure. I like to give each atom the total number of Lewis dots that it would have in a neutral atom. And then we form our single bonds, and if we have an ion, we add or subtract electrons, and it doesn't matter from where. And then we pair up the electrons to give us double or triple bonds if necessary. But at the end, we have to remember that each atom has to have a filled octet, except for some of the exceptions being hydrogen and fluorine. Hydrogen only has 2 electrons. Fluorine can have 8 but never be expanded. Some elements have expanded octets, like sulfur and phosphorus. They can have expanded octets. And remember, those are row 3 and lower on the periodic table. So if we follow these steps, they'll give us legitimate Lewis dot structures. And then we should check the formal charges, or we should get the formal charges for each atom by using a fairly straightforward formula that says you take the number of electrons in that neutral atom minus 1/2 of the bonding electrons in your structure minus the total number of unpaired electrons in that structure, and that'll give you the formal charges. In the end, the formal charges of all the atoms should equal the total charge on the structure. If it doesn't, you've done something wrong, or you've calculated your formal charges wrong. So, for example, let's write a possible Lewis dot structure for HNO3. If you want, you can stop the tape right now and you could draw something you see there, or something, and see if it's correct. So nitrogen is going to be our central atom. In this case, I would probably give you the structure and say, okay, we're going to have the 3 oxygens attached to the nitrogen, and then we're not going to have that hydrogen just hanging out there. We're going to have the hydrogen attached to the oxygen. And it doesn't matter which one. So the oxygen is going to be, this oxygen will be attached to that hydrogen. So now we put in our total number of valence electrons for each of the atoms. Oxygen has 6 valence electrons. I already put that bond in. So there's our 6 valence electrons for that oxygen. I'll go ahead and put 6 valence electrons in for this oxygen, 6 valence electrons in for this oxygen, and then nitrogen is a group 5, and so we'll give nitrogen 1, 2, 3, 4, and 5 electrons. And so we go ahead and form our single bonds. I already had one here for the hydrogen. We'll form that single bond. Let's pair up these 2 to form the NO single bond, these 2 to form the second NO single bond, and how about these 2 to form the third NO single bond. So let's clean that structure up down here by writing the nitrogen to the top oxygen like so. The nitrogen to that oxygen, and then the nitrogen to this oxygen, and then don't forget the lone pair on the nitrogen. Okay, so now we have to ask ourselves, do all of the atoms have filled octets? And the answer is no. This hydrogen is okay. It can only have 2 valence electrons, so it's okay. This oxygen is sharing 8 electrons, so it fulfills the octet rule. This nitrogen is okay. It's got 2, 4, 6, 8 sharing electrons, so it's fine right now. But this oxygen only has 7, and this oxygen only has 7. And so what are we going to do about that? Well, here's what we cannot do. We can't pair up this electron on the nitrogen and this electron on the oxygen, because that would give the nitrogen 10 valence electrons, which violates the octet rule, and nitrogen cannot form an expanded octet. So how am I going to handle this? Well, let's do this. Let's pick this electron up from the oxygen and let's give it to this oxygen. You can say, can you do that legally? Sure. The idea here is that the electrons, basically, this whole total molecule has X number of electrons, and we can distribute them around the molecule. And some people draw their Lewis dot structures that way. I like to give each atom, its amount first, and then if you have to move them, you can move them. But that would be perfectly legitimate. So if I do that, and one thing you have to do is be careful not to lose them along the way, or turn 1 into 2. Okay. Now if I do that, this is going to be my resulting Lewis dot structure. And so now what I've done is I've given this oxygen a completed octet, but at the expense of this one. But now I can remedy that whole situation by taking this pair of electrons on the nitrogen and forming a double bond. So my final structure, one of my final Lewis dot structures that's possible, would be to have this as the Lewis dot structure. Now all of the atoms have filled octets, and everything is okay for this molecule in the Lewis dot structure that I've written. Now after we write a legitimate Lewis dot structure, we should assign formal charges. And so assigning the formal charges, we can use the formula for, let's say, this hydrogen. This hydrogen has 1 electron in its neutral atom, minus 1/2 the number of bonding electrons would be minus 1/2 of 2, and so it would have a charge of 0. Now there's another way to look at formal charge, and I'll show you that in a moment. So for this oxygen calculating its formal charge, we would have the number of valence electrons in a neutral oxygen atom, which was 6, minus 1/2 the total number of bonding electrons, which is in this case 4. So 6 minus 1/2 of 4, minus the total number of non-bonding electrons, which is also 4. And so we have a 6 minus 2 minus 4, and so this oxygen also has a 0 formal charge. So you can use that formula, that works fine. Now, another way to do this is to think about how many electrons did that oxygen own when it formed the molecule. So how many did it come with? And oxygen came with 6 valence electrons. Now, how many does it own in the final structure? And ownership of electrons means this. If you're lone pairs are owned totally by the oxygen. Bonding pairs are half owned by the oxygen and half owned by the hydrogen. So that if I looked at how many electrons this oxygen owns in the final structure, it owns these 4 outright. It owns 1 of these 2 to the hydrogen and 1 of these 2 to the nitrogen. So therefore, it owns a total of 6 of the 8 valence electrons, and it shares 4 of those. So in this case, it came with 6 valence electrons. It owns 6 electrons at the end. That would give you a formal charge of 0. Okay. we look at this oxygen down here, what's its formal charge? What do you say? I say 0. Because this oxygen came with 6 electrons, it now has 1, 2, 3, 4, 5, 6, no change. Down here, this nitrogen, what's its formal charge? Give you a second to answer. Well, it came with 5 electrons. How many electrons does it own? It owns 1, 2, 3, 4. Therefore, it has a +1 formal charge. It lost an electron. Who did it lose the electron to? This oxygen. Well, sort of. It lost an electron along the way. What is the formal charge on this oxygen? Well, it came with 6. It now owns 2, 4, 6, 7. It's picked up an electron along the way, and so it has a -1 formal charge. So if I come down here and I write this Lewis dot structure with its formal charges, all of this oxygen has a formal charge of 0, the hydrogen 0, this oxygen 0, this nitrogen +1, and this oxygen -1. Now, do all the formal charges add up to the overall charge on HNO3, nitric acid? Yes, because they add up to 0. Nitric acid is a neutral molecule. Okay. So we've written a legitimate Lewis dot structure for nitric acid. Is that the only possible Lewis dot structure that I could have written for the atoms attached in this format? And so in other words, having this oxygen attached to this hydrogen, having the nitrogen attached to the oxygen on the left, and the oxygen on the bottom. Is that the only possible Lewis dot structure that I could have written? Well, no. What if I would have taken the situation over here and done the reverse, taken this electron, given it to this oxygen? Then what structure would I have ended up with? I would have ended up with this Lewis dot structure. The nitrogen-oxygen single bond would have been to the right-handed oxygen, and the double bond would have been to the oxygen at the bottom. Now understand that these two structures, I didn't change the position of the hydrogen. If I changed the position of the hydrogen and bonded it to any of the other oxygens, that's a totally different process. These two structures right here only differ in the placement of the double bonded pair of electrons, the electrons for the double bond. Here they're to the right-handed oxygen, down here to the bottom oxygen, and a placement of one lone pair. In this case, the oxygen at the bottom has that lone pair. Over here, the oxygen to the right has a lone pair. So these two structures only vary in the placement of the multiple bonded electrons and the lone pairs. And that's a special relationship. And that's what we call resonance structures. So resonance structures are defined as two structures that only differ in the placement of multiply bonded electrons and pi electrons, and lone pairs. Later on, I'm going to call them multiply bonded electrons pi electrons. Okay. And we indicate the two molecules are resonance structures by using a double-headed arrow. Okay. So these two resonance structures, if I go through and I look at my charges, this nitrogen still only has 1, 2, 3, 4 electrons, so it still has a +1 charge. This oxygen over here now has the 6 valence electrons, so I picked up 1 to become -1, and all the other atoms have their 0 formal charges. And so what you see is that in resonance structures, the charges could be on different atoms. In this case, the bottom oxygen is a -1 charge. Over here, the right-handed oxygen has the -1 charge. Okay? So here are two legitimate resonance structures that can be written for nitric acid. Okay? And they differ by the placement of the multiply bonded electrons, the double and triple bonds, and the lone pairs. And also the charges then could be different. Okay, and that's the idea of resonance structures. Now, we could do the same thing for the phosphate ion, the PO43 minus ion. And if I do that, and if you want to take a minute, stop the tape and go ahead and draw out, in this case, the phosphorus is going to be attached to 4 oxygens. So how many different resonance structures can you draw? And in this case, the phosphorus could have 4 bonds, or it could have 5, because phosphorus can form an expanded octet. But let's write all the possible structures for the phosphate ion. So if you want, stop the tape, draw them out, and then I will draw them out here and we'll see if you're correct. Okay, here's the 5 that I drew. Hopefully you drew this 5 as well. Now, let's go ahead and put in our formal charges for these 5. First of all, I'll come to the rules of resonance here in a moment, but one of the things we have to realize is that resonance structures must also obey the octet rule. And so you can't write a resonance structure that does not obey the octet rule. Now in phosphorus's case, phosphorus can have an expanded octet and it can share a total of 10 electrons, which means it can have a total of 5 bonds. And so 4 of these resonance structures have phosphorus in its expanded octet, and the 4th one has, and the 5th one over here has phosphorus having just 8 valence electrons that it's sharing. So let's go ahead and put in the formal charges. Again, if you want to stop the tape and draw the formal charges to see if you can do it, hopefully you can, then go ahead. But this oxygen would have a -1 charge, -1 for this oxygen, -1 for this one, and -1 for that one. Why? Because this oxygen has 2, 4, 6, 7 electrons. It came with 6. It now owns 7. Or you can use the formula that it had 6 minus 1/2 of 2 minus 6, and you get a -1 charge. Now for the phosphorus, phosphorus is a group 5 element, so it came with 5 valence electrons. It now only owns 4, and so we have a +1 charge there. Does everything add up? We got a +1, 4 minuses, so overall the charge is -3. Yes, everything adds up. Coming over here, I forgot to put the lone pair on the oxygen there with the double bond. This oxygen has a 0 formal charge because it's got 2, 4, 5, 6. Came with 6, got 6, no change. Down here with the oxygen, we got a -1, another -1 charge here, and a third -1 charge there. And after you do this enough, what you'll begin to realize is an oxygen that's doubly bonded with 2 lone pairs has a 0 formal charge. An oxygen with a single bond and 3 lone pairs has a -1 charge. How about the phosphorus in this case? Well, hopefully if I've got 3 -1 charges, that phosphorus better be 0, and it is. It's got 1, 2, 3, 4, 5, and it came with 5. So what you can see for these other 4 resonance structures is that the oxygens with the single bonds are all -1s, and then the phosphorus and the other oxygen with the double bond have 0 formal charge. And so I could go in here and I could put in all of my formal charges. Now we'll get to a point where we won't write 0 formal charges. We'll only be interested in those atoms that have a non-zero formal charge. But for the moment, let's put in the 0 formal charges. So here are my 4 resonance structures. And again, are they all legitimate? Yes, because none of them violate the octet rule. Okay. If I go back to the nitric acid, are these 2 legitimate resonance structures? Yes, they don't violate the octet rule, and all of the atoms have filled octets. You may ask yourself, well, what does that mean for these structures? Aren't some of these structures the same? And the answer is no, they're not the same. The structures are different. And what you have to realize is that when you're looking at resonance structures, there's some things that you're not allowed to do, and there are some things that you are allowed to do. You are allowed to move lone pairs and pairs of electrons that are involved in multiple bonds. You are allowed to move those as long as you don't violate the octet rule. One thing that you're not allowed to do is you're not allowed to move atoms. So all the atoms have to be in exactly the same position throughout all of the resonance structures. So for instance, let's say for this first resonance structure that I call this atom A, this oxygen B, this oxygen C, and this oxygen D. And over here, this would then be oxygen A, oxygen B, oxygen C, and oxygen D. So are these 2 structures different? Yes, they're different. How would I know that? Well, in this case, the phosphorus has 4 PO single bonds. And over here, it's got 3 PO single bonds and a PO double bond. And you might say, well, that's easy enough to see. I get how these 2 are different. And the reason that we would say they're different is let's look at the multiple bonds and the charges. For instance, oxygen A here has a -1 charge. Oxygen A here has a 0 charge. So if I was going to differentiate between these 2 structures, I'd say, well, in this case, oxygen has a -1 charge, and over here it's got a 0 charge. That's easy enough to tell that the 2 structures are different. If you also remember from general chemistry, bond lengths between single, double, and triple bonds also differ. A single bond is the longest bond. A double bond is shorter. And a triple bond is the shortest of the bonds. Why? A couple of explanations. We'll talk about what's called S character later on. But basically, if you kind of think about this, the 2 atoms or the 2 nuclei that are sharing a single bond, they have 2 electrons that are simultaneously attracted to the 2 nuclei. And so there's some electrostatic attraction there. When you get to 4 electrons that are being shared by those 2 nuclei, the attraction to the nuclei becomes stronger, and it sort of pulls them together. And with the triple bond, it pulls them together even more. So you get the shortest bond of a triple bond, and the shorter double bond, and then the longest single bond. So in these 2 structures, I can tell the difference between the first structure and the second structure by looking at the PO bond length. And this PO bond length would be a single bond. This would be characteristic of a double bond. Now, what really starts to sort of confuse people when you first talk about resonance structures is if I took these 2 structures in the middle here, and let me see if I can draw a box to sort of isolate them. Are these 2 structures the same? Let's define same. If you mean, are these 2 the same structure? No. Again, this is oxygen A, this is oxygen B, this is oxygen C, that's oxygen D. Are these 2 the same structures? No, because up here, the POA bond is a double bond, and down here, the POB, the B oxygen, is the double bond. So just looking at the P to O A, what we call oxygen A here, this is a double bond, this is a single bond, this is a longer bond, this is a shorter bond. Look at the charges. Oxygen A in this case is a 0 charge. Over here, oxygen A has a -1 charge. The P to OB single bond is different than the P to OB double bond. They'd have different lengths. This oxygen would be 0 formal charge. Over here it would be a -1 formal charge. The other 2, same bond length, same charge. But the phosphorus to oxygen A, phosphorus to oxygen B are different. Remember that in resonance structures, or remember, this is something I told you, in resonance structures you're not allowed to move atoms. And so when I call this oxygen A, I can't just simply flip the molecule around to turn oxygen A into oxygen B. That's not allowed. So are these 2 structures different? Yes. If I call this structure number 1, structure number 2, structure number 3, structure number 4, and structure number 5, are structures 2 and 3 different? Yes. Are structures 3 and 4 different? Yes. Are structures 4 and 5 different? Yes. Are all 5 of these structures different? Yes. How are they related? I can move electrons, both the multiply bonded electrons and the pi electrons, to convert one structure into another. And I'll do that in a few minutes. Okay, but just accept for the moment that these 5 structures are different. It's easy to see the difference between 1 and 2, or 1 and 3, 1, 4, and 1, 5. A little bit harder sometimes when people start to accept the fact that 2, 3, 4, and 5 are different, but they are. If I go back to my nitric acid, if I call this structure 1 and this structure 2, are those 2 different structures? Yes. Why? The nitrogen to the right-handed oxygen is a double bond here, a single bond there. This oxygen 0 formal charge, this one -1. Same thing as what we did with the phosphates. Okay, so structures 1 and 2 are different structures. Okay. Now let me stick with this nitric acid example. While they're different structures, are they of equal stability? Are they equally stable in terms of them being structures? Now that's a whole other question. Okay. And in order to answer the question of whether or not 2 structures have the same energy or have different energies, we have to talk a little bit about how we rank resonance structures according to their stabilities. What criteria do we use? And so if we go to, let's first of all talk about the rules of resonance here, and then we'll talk about how we can differentiate between resonance structures in terms of their energy. Because I've already shown you two examples of how we can differentiate between resonance structures according to their structure. So these are what I call the rules of resonance, and actually they're not what I call the rules of resonance. A textbook that I taught out of 20 years ago coined this phrase, rules of resonance. Your textbook has a very similar set of rules in it. But one of the things that we're going to find is that resonance forms are imaginary. They're not real. The true structure of the molecule is what's going to be what's called the resonance hybrid. And I'll come back to that in a minute. But we've already seen this, that resonance forms or resonance structures differ from each other only in the placement of their pi, which means the multiply bonded electrons, or the electrons involved in the multiple bonds, be it a double or a triple bond, which we'll later on this week remember that those are pi bonds, or the non-bonding electrons. So that's how they differ. It's only in their placement. Of course, the difference in the placement of the multiply bonded electrons gives you a difference between a single bond, a double bond, and a triple bond. Different resonance forms don't have to be equivalent. And by equivalent, I mean equivalent energy. One may be more stable than the other, and so we'll have to talk a minute here about what's the resonance hybrid and how these things, what we call, contribute to the resonance hybrid. So we've seen this example, that resonance structures differ by their placement of their multiply bonded electrons and non-bonding electrons. I've also stated that the resonance structures have to obey the octet rule, or what we call the normal rules of valency. So you can't have in a resonance structure an atom break the octet rule. And I'm going to define breaking the octet rule here by having more than what it's allowed. Can it have less? Yes. And there'll be a consequence for that. So we've seen that. Okay, so now what we need to do is we need to learn about this resonance hybrid. And so let me go back here to my nitric acid example. And I'm going to pull up a blank screen here to look at the nitric acid. So if I quickly redraw the two resonance structures for nitric acid, here's structures number 1 and 2. They're resonance structures, so I'm going to use the double-headed arrow to show the difference between the two of them. And I'm going to draw in the non-zero formal charges, a +1 for the nitrogen and -1 for the oxygen. Now, if I had these two structures, ultimately the question that came about when people first started to draw Lewis dot structures was, they said, which of these two structures is legitimate, or are they both the same? And then they asked a question of, if I have these two structures, which one would I actually find for nitric acid? So if I had a microscope that could look at an individual atom, which those actually do exist, if I had that microscope, what structure would I see? Structure 1 or structure 2? Okay, and that was a big question. Back in probably in the 1910s, people had this question about what was the true structure of resonance structures. And the ultimate answer that came about was that neither one of these structures was the correct structure. The correct structure was what we call a hybrid of the two. And so, you know, you learn about the term hybrid for cars, for biology. It just basically means something that's a mixture of two different things. Now, originally, people thought that these two resonance structures might be constantly flipping back and forth between the two forms. And that was found out to be quickly not the case. I like to give the example that if I had a hybrid between a pit bull and a chihuahua, as cool as it would be, that hybrid puppy is not going to be constantly switching back and forth between a pit bull and a chihuahua. That'd be interesting to see, but that's not going to happen. And so, you know, if you've ever studied genetics, you have a mixture between the two. And so that's what's going to happen with these two structures. The true structure is what we call the resonance hybrid. So the question is, how do we draw the resonance hybrid? Well, to draw the resonance hybrid between two structures, what I'm going to do is I'm going to draw the core connectivity between the atoms. So in other words, I'm going to draw with single bonds how the atoms are attached. In other words, what is common in these two structures. Now, when I draw a resonance hybrid, I leave out the lone pairs. I'm only going to place charges and single and double bonds, or single and multiple bonds around the atoms. I'm going to leave the lone pairs out. So this is what's common in these two structures of nitric acid. Okay. Now what I'm going to do is I'm going to average the bonds. So between the oxygen and hydrogen up here, I got two single bonds, average single bond. Down here, I got a double bond and a single bond. Well, let's start with this nitrogen to top oxygen, single bond, average is a single bond. Now, nitrogen to right-handed oxygen, double bond, single bond. What's the average there? Well, we're going to take a more generic approach and say that the average between a single bond and a double bond is something between a single and a double bond. You might say, well, it doesn't make any sense. How are you going to represent that? I'm going to represent something between a single and a double bond by writing a dotted line to indicate a partial double bond. And so when you see a dotted line, that's going to indicate a partial bond. So this bond is somewhere between a single bond and a double bond. Okay. Is it exactly 1.5 bonds? In this case it is going to be, but in general, I don't care. I just need to know that it's between a single and a double bond. How about the nitrogen to the bottom oxygen? It's an average between a single and a double bond, and so I'm going to use a partial double bond there. So now what I've done is I've averaged my bonds. Now let's do the same thing for charges. Hydrogen and oxygen up here, 0 formal charge, 0 formal charge. This nitrogen is +1 in both structures, so it needs a +1 formal charge there. That's the average. Now what about the oxygens? Well, if we look at the right-handed oxygen, we've got 0 formal charge and we've got a -1 formal charge. And so what's the average there? Well, normally you might say a half, but again, we're not concerned about the exact number. We're concerned about the fact that it's somewhere between 0 and -1. And so the way I represent that is I use a delta minus charge. And so I say the right-handed oxygen has a delta minus charge. That means it's somewhere between 0 and -1. I don't really need to know the exact number. How about the bottom oxygen? What's the average between -1 and 0? Delta minus as well. Okay. Now, looking at this structure, these two delta minuses, they need to add up to be -1. And in this structure, they're actually each minus a half. But let me come back to that in a moment. Okay. So here's the resonance hybrid of nitric acid. And normally for the resonance hybrid, I will put sort of a bracket around it. Okay, so there's the structure. There's the resonance hybrid. That is the true structure of nitric acid. In nitric acid, we've got a nitrogen-oxygen single bond, an oxygen-hydrogen single bond, and then two partial nitrogen to oxygen double bonds, with those two oxygens each having a slightly negative charge. Okay, and if I didn't say this delta term, delta means partial in organic as well. So this is a partial negative charge. Okay, so there's my resonance hybrid. And that's the true structure. Okay, so that's what people found when they addressed the issue of two possible Lewis dot structures. What's the true structure? The true structure is the resonance hybrid between them. Now, that still doesn't answer a question of what about structure 1 and structure 2? Well, you could say, I don't really care about those. I only care about the resonance hybrid, the true structure. But we do have to worry about these two structures, because what we're going to find is we're going to find that one of the structures may contribute. And that's the term we use. It may contribute more to the formation of the resonance hybrid. So what's going to tell us what structure contributes more to the resonance hybrid? The resonance hybrid is going to look more like structure 1 or structure 2. It's not a foreign concept, because, take kids. Do kids look more like one parent or the other? Okay, same thing here. So how do we know if which one of these two structures contributes more to the resonance hybrid? What's the resonance hybrid going to look more like? Structure 1 or structure 2? Well, in order to determine the contribution, we need to know what the energy or stability of these two resonance structures are. Okay, so what's their energy and what is their stability? Well, if we go back to this issue of the rules of resonance, we've now taken care of the other 3 points here. The resonance structure, they're imaginary. They're not real. The true structure is the resonance hybrid. Okay, that's what people have found. Different resonance structures don't have to be equivalent in energy. One may be more stable than the other, and the one that's the most stable is what we say contributes most to the resonance hybrid, meaning that the resonance hybrid will look most like that resonance structure. Okay? And the resonance hybrid is the most stable structure of any of the individual resonance structures. So the resonance hybrid is more stable than any other resonance structure. That kind of makes sense. The only thing here is, so how do we know what the more stable resonance structure is? Well, fortunately, we've got 3 sets of rules, or 3 rules, that we can use to judge the stability of the resonance structures, what we could call resonance contributors. And these are in order of importance. So in other words, we use rule number 1. If the 2 structures or 3 structures or 4 or 5 structures are still tied after rule number 1, we go to rule number 2. If they're still tied after rule number 3, we go to after rule number 2, we go to rule 3. If they're still tied after rule 3, then we say they have equal stability, or their energies are identically the same, which means that they will each contribute the same amount to the resonance hybrid. So the resonance hybrid will basically be an average of those 2 structures, and I'll show you that for the nitric acid, because if you're thinking, well, that's exactly what happened in the nitric acid case, that's true. So rule number 1. Rule number 1 says each atom should have a completed octet. Resonance structures that don't have every atom having a completed octet are less stable immediately by rule number 1. Does it mean that we draw them? Sometimes we will and sometimes we won't. So sometimes I'll say write all the possible resonance structures that you would get having completed octets. Sometimes we won't. Okay, so that's going to depend. So that's rule number 1. If they're tied there, we go to rule number 2 that says structures should have 0 formal charges. The most stable structures have 0 formal charges. Otherwise, small charges are preferred over big ones. So it'd be better to have just one -1 charge in the structure than to have a -2 or a +2. It would be better to have than, a +1 -1 combination than a +2 -2 combination. So the idea is we have best case scenario, no formal charges, or we have small charges and a small number of small charges. Okay, and that can be a little tricky. If they're still tied, then we go to rule number 3 that says the formal charges should agree with electronegativity. What that means is if in 2 resonance structures you have a nitrogen having a -1 charge in one case and a carbon having a -1 charge in the other case, you would like to have the -1 charge go with the more electronegative of the 2 atoms. Okay, so if you have -1 on a nitrogen, I'll write this down. If you have -1 and your choice is to put it on a nitrogen or a carbon, that -1 charge would go with the most electronegative of the 2 atoms. Now, carbon and nitrogen are in the same row. Nitrogen's closer to fluorine. Therefore, nitrogen's more electronegative than carbon. Problem solved. The -1 charge should go with the nitrogen and not with the carbon. So that's the third and final tiebreaker. After that, for all intents and purposes, we consider the structures to be identical in energy. Okay, so those are the 3 rules we use. Completed octet, small charges, and then put the formal charges with the electronegativity. All right, let's go to our nitric acid example. Which one of these 2 structures is more stable, number 1 or number 2? Take a minute. What is it? Okay. In this case, do all of the atoms have completed octets? Yes. Do both molecules have a small number of charges? Yes. A ±1, ±1 down here. They have identical charges and the identical numbers of those charges. In this case, the -1 charge on this oxygen, the -1 charge over here is on this oxygen. They have identical electronegativities. Therefore, I conclude that structures 1 and 2 have equal energy, or they have the same energies. Now notice, same energy is not the same as same structure. So they have the same energies. Okay. So what does that mean? That means that the resonance hybrid of nitric acid would basically be an average of these 2 structures. So this oxygen would really be -0.5 in terms of charge. And this oxygen would have a -0.5 charge. And the nitrogen-oxygen bonds would be each perfect 1.5 bond lengths. Okay, so in this particular case, which is sort of an exception, when you have the 2 resonance structures being identical in energy, the resonance hybrid is going to be exactly the same. It's going to have it's going to be an average of those 2. Okay, and we could put numbers to that. But in general, that's not the case, and it's really difficult to put numbers to it, which is why we use partial bonds and partial charges. Okay. Let's go back to the other example that we looked at. Phosphate. Take a minute. Which of the phosphate resonance structures have identical energies? Which ones have equal energies? Got it? Two, three, four, and 5 have the same energy. Why? Because in all these cases, you've got first of all, the phosphorus has an expanded octet in every one of these cases, so it fulfills the octet role. All the oxygens have completed octets, and all three of these have 3 - 1 charges on the oxygens. The number of charges are the same, the charges themselves are the same, and the electronegativities of those charges, they're all on oxygens. So therefore, I would conclude that 2, 3, 4, and 5 all have the same energy. Okay. Now, compare any of those to number 1. Are those structures more stable than number 1 or less stable than number 1? Number 1 is the least stable resonance structure. Why? Well, phosphorus still has a quote-unquote completed octet, but by it not expanding its octet, what happened? There's an additional +1 and -1 charge. So there's more charges in this molecule, in this resonance structure, than there are in resonances 2, 3, 4, and 5. And so therefore the resonance hybrid would most likely resemble an average of 2, 3, 4, and 5, and number 1 would contribute very little to its resonance, to the resonance hybrid. Okay. And if we were to write the resonance hybrid of numbers 2, 3, 4, and 5, could you do that? Its resonance hybrid of just 2, 3, 4, and 5 would look like this, right? You would have a partial double bond to all 4 oxygens and delta minus charges on all 4 of those oxygens. Okay, so there are the whole idea here is that there are oftentimes more than one legitimate resonance structure. And when we have those situations, we most likely have resonance structures. When we have resonance structures, we need to write all the possibilities that are legitimate, right, that follow the rules of valency. And then we need to sometimes the first step is to rank them in energy and then write the resonance hybrid that has contributions from the most stable of those resonance structures, of the major resonance contributors. Okay. So hopefully that's a review of general chemistry in terms of drawing resonance structures to draw the resonance hybrid, which you just simply draw the core structure, which will involve single bonds, average out all the bonds, average out all the charges. Average bonds are represented by a delta, or by dots, by dotted line. Average charges are represented by a delta. Could you do that for NO2? Okay, well, try it, and I'll post an answer online, or we'll do this one in class. Maybe I'll call on people and ask them what structures they got for NO2. How about OCN minus? Why don't you try that one for class on Friday. Okay. All right. So that's the basics of resonance structures. As you go through and look at this in a textbook, if there's something that didn't make sense, that's what we will do on Friday after our quiz over the syllabus. We'll talk about, if you have questions, ask, and we will go over that. And I will ask somebody, what did you get for NO2? Can you write the legitimate resonance structures for NO2 minus? Can you write then the resonance hybrid? Can you tell me which resonance forms or structures are the major contributors of NO2? Which one's a minor contributor? They're both the same in terms of energy. How about OCN minus? Okay. For the NO2 minus, we're going to have a nitrogen attached to two oxygens. The nitrogen, being the least electronegative element, will be in the center. In the OCN case, we've got oxygen attached to carbon attached to nitrogen, and in that case you've got a -1 charge, so your formal charges all have to add up to -1. So try NO2 minus for Friday's class, try OCN minus for Friday's class, and we'll see what the answers are. And if you don't know where to start, then come and see me or ask in class, and we will go over these. Now, the last topic that the book kind of throws into this mix is very quickly the idea of molecular formulas, empirical formulas, and then the idea of structural formulas. And let's look at these in an organic context, not necessarily in a general chemistry context. Because one of the things that you do in general chemistry a lot is you just simply write the molecular formula of the molecule, or actually the molecular or empirical formula. So the differences between these are that the molecular formulas gives the identity and total number of atoms in each molecule. Well, we could take NaCl, and NaCl would be a formula for sodium chloride. I technically cannot use the word molecular formula because if you remember from general chemistry, NaCl is not a molecule, because NaCl can basically, you can have a crystal of NaCl that can exist as big as the amount of sodium and chloride ions that you have. There's no definitive stopping point for NaCl. So we just say formula. But if we had a molecule of an organic molecule, we might have something like C6H6, which is a famous molecule called benzene. Later on, I may tell you the story of how people used benzene to, that was a big issue of the different resonance structures that you could have for benzene and what the resonance hybrid of benzene looked like. That was a real big point of controversy back as late as the 1910s. So C6H6 just means that a molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms. That's all it says. In general chemistry, that would have been good enough, but that's not going to be good enough in organic. We're going to need to draw out the structure of it, the Lewis dot structure. Tell me where the multiple bonds are, if there are some. Tell me where the hydrogens are attached to the carbon. We're going to need to draw a structure of benzene. So in general chemistry, you do lots of things with molecular formulas. We're not going to do that in organic. We're going to actually draw structures. Now, just along this line, the difference between a molecular formula and an empirical formula is this gives you the exact number of atoms in the molecule. The empirical formula just simply gives you the ratio. So the empirical formula of benzene would be CH, because you can divide by 6. The empirical formula, if you go back a year to general chemistry, the empirical formula is what you got from things like combustion analysis, where you had problems that said so many milligrams of this molecule gave X number of grams of CO2 and X number of grams of water, and you had to calculate back what its empirical formula was. Empirical formula is useful, but not that useful for what we're going to do in organic. what's most useful is the structural formulas. So when we draw Lewis dot structures, we are drawing structures and structural formulas. I'd like to know how many lone pairs there are, where they're at, what kinds of bonds are between atoms, and so that's the type of structural, the structures that we will draw. Now, there's different types of structural formulas depending upon, in essence, how lazy you are. Here's a couple of structures of ethyl alcohol. Ethyl alcohol, grain alcohol, ethanol has a molecular formula of C2H6O. That's not very useful to us. What we'd like to know is how the atoms are attached in ethanol. And so here is one way to draw the structure. And if I put two carbons in here and I put the lone pairs on the oxygens, I in essence have a Lewis dot structure. It tells me that these three hydrogens are attached to that carbon. There's a carbon-carbon bond, a carbon-oxygen bond, two lone pairs on the oxygen, and then the oxygen is attached to one hydrogen. So this is, in essence, what we've been drawing as Lewis dot structures. Now, there is what's called the condensed formula, where I take this Lewis dot structure and I condense it down into this formula over here. So this is sometimes called a condensed, let's just start over again, a condensed structure. It's written CH3CH2OH. How did I get that from the Lewis dot structure? Well, what I did was I took this group, which I called a carbon with three hydrogens attached to it. That's attached to a carbon with two hydrogens attached to it, which is then attached to an OH group. And so that's how we get the condensed structure. The condensed structures were useful when I had a typewriter and I needed to type out a structure. Then I could just simply write CH3CH2OH. Now, how do you get from here to here? Well, what we have to remember is that hydrogens always occur on the outside of the molecule because a hydrogen cannot have more than one bond. And so how would I take a condensed structure and make it into a Lewis dot structure? I would just simply take the non-hydrogen atoms, attach those together, and then say that carbon's got three hydrogens attached. This carbon in the CH2 has two, and there's the OH. So it's relatively straightforward to convert from a condensed back into a Lewis dot structure if you remember that hydrogens have to occur on the outside. And your book will print a lot of these, a lot of those structures, simply because it's easier to type and you don't have to draw out the structure. Okay, so Lewis dot structures, condensed structures. The third that we're going to be using a lot are what I like to call line bond. I think your book uses the term line angle. There's lots of terms for this. But it's going to be really tedious to draw out Lewis dot structures because showing every explicit carbon-hydrogen bond in the molecule is going to get really tedious when I've got 6 or 10 or 20 atoms. So the condensed is like the lazy version of that. And then if you really want to be lazy, then you basically draw the line bond structure. So in the line bond structure, every end of a line indicates a carbon atom, and every intersection between two lines indicates a carbon. And we don't show hydrogens. So therefore, what you have to do is you've got to say, okay, this is the end of a line, there's a carbon here, this is the intersection of a line, there's a carbon there, and now I have to give it enough hydrogens to make 4 and only 4 bonds, unless a carbon has a charge on it. Okay, but we'll start with molecules that are neutral, or carbons that are neutral. They have no formal charge. So you add enough hydrogens to give carbon 4 and only 4 bonds. Okay. So in this case, this carbon has 1 bond, 2 bonds, 3 bonds, 4 bonds. This carbon has 2 bonds, 1 bond, 2 bonds. And then typically I'll show, if it's a non-carbon atom, I'll show the hydrogens directly attached to nitrogens and oxygens and sulfur and the like. Okay. So these are the 3 types of structures that you'll see. Lewis dot structures, explicit, that's the most tedious. Condensed is a little bit easier, and the line bond structures are the ones that will end up drawing the most. And again, the line bonds are very simple, and you can actually see examples on the first page of the chapter. They put line bond structures. You'll see line bond structures in the lab book. And so being able to convert back and forth between line bond and condensed structures, or line bond and Lewis dot structures, will become relatively easy, though at some point you'll just begin to see a CH2 group here or see a CH3 group here as you get more familiar with drawing out the structures. And I'll just simply add that, if we wanted to draw an organic, a general organic structure of a steroid, it is a lot easier to draw the structure like that and begin to write things like OH groups here and CH3 groups there, or put double bonds. It's easier to draw the line bond structures and a lot faster than it is to draw out the Lewis dot structures for this. Although I think in the homework problems, they'll be converting from this structure to the line bond structure. I'll have a couple of those for you so that you can get used to that nomenclature, or that way of drawing structures. Okay. All right, so that is the end of the lecture for Wednesday, August 29th. We will, our Friday quiz then, there will be a Blackboard online quiz over the material that I've talked about in the lecture, as well as the reading material that will be due before class on Friday. And on Friday's quiz will be over this material after we've talked about it in Wednesday's lecture. So Friday's quiz will be over Wednesday's lecture material. Wednesday's quiz, since you're watching this before Wednesday, will be a quiz on the syllabus.